welcome and introduce Luhao Zhang, who's an assistant professor in Johns Hopkins University. She did her PhD 2 years ago in Austin, Texas, and then she was at Columbia for just 1 year before moving on to Johns Hopkins. And she will talk today about a class of interpretable and decomposable multi-period convex risk measures. And Luhao, the floor is yours.
Okay, thank you, Yang, for this nice introduction. I also want to thank the committee for this kind invitation, and thank you everyone for attending this talk. It's a great honor to be here, and I'm very excited to share some ongoing work with my collaborators, Ray and Jinchen, on the multi-period convex risk measures. So myself also is new to this area, so any comment, feedback, and questions are very welcome. So let's start with some fundamental objectives that we are working on this object. So the risk measure here, intuitively speaking, a risk measure rho could be regarded as a function maps from some financial position to a real numbers that quantify the risk. So this value could also be some extended real numbers that accounts for some extremely loss, right? So for this one stage risk measure, like many literature has well discussed this scenario, and let's think about how can we extend this idea to the multi-period setup. So again, how to formulate the risk in multi-period has been largely discussed in the past literature. At least two formulations could be there are at least two common ways to measure this risk of a random sequence. So for all this talk, I will focus on the discrete time period risk measures instead of the continuous time setup. So one of the well-known, which we call it the end of horizon approach, it means that we can measure the risk of the sum of all this random sequence, x1, x2 goes to x capital T. So this approach actually is a straightforward extension from the single period case and has a clear interpretation. So for example, we can apply this conditional value at risk, the CVAR of the sum to measure the risk, to measure their risk, right? And also, on the other hand, for many choice of the risk measure, it's not clear whether this end of horizon approach could be decomposed into components over different time periods. This is also what we call the time inconsistent issue, which would be an issue, especially from the perspective of decision theory. So that may imply an irrational behavior for each of the time steps. So to avoid that, some of the approach may think about, okay, how about we just formulate this question to compose every single period risk measure into this conditional way, and then put them together into this nested approach. So as you can see, by this construction itself, it actually enables the dynamic programming. So, and also it's more computationally friendly, because we can just calculate the risk for each of the steps and then do it into this nested way. However, the question is that what's the equivalent end of horizon representation? It's often abstract and may not have a clear interpretation. So for example, this composition of the CVAR, sometimes we can call it the iterated conditional tail expectation. It actually does not have a simple interpretation of the end of horizon formulation. So, and also on the other case, when we do it in practice, sometimes may be too conservative. Let's take the CVAR example again. As you can see, it actually measures the tail risk of the tail risk of the tail risk, right? So it may be too conservative and conservative to consider the risk of them as a whole group, right? So when we can think about it is that how can we find a class of multi-period risk measures that are both interpretable and decomposable? Because we also want our risk measure to provide clear and intuitive insight, and also they should allow us to do some they should also allow us to break this risk down into different time period and make them useful for the decision making at each of the each of the stage, right? So to answer this question, in the past literature, there are actually some existing or proposed already try to address this question. So to introduce, this is what we call the entropic risk measure. To introduce this approach and also our proposal, I will first quickly review what's the fundamental property we want our risk measure to have, and also to have this robust representation enable us to write this dynamic risk measure to be a problem of the evaluating the worst case scenario, and how this entropic risk measure could address this question. However, it also relies on the requirement of what we call the low invariance, why it would be an issue, especially in the data-driven scenario, and how our proposal could address this issue without the dependence on this requirement. So that's the outline of today's talk. So let's just quickly review some fundamental properties we usually want our risk measure to have. So the monotonicity like the financial position, or if one of the financial position always incurs more loss than the other one, then they should have the higher risk, right? And also the risk measure should have the same unit of the money. If I combine the position, the risk should not increase. And also if I scale my position, the risk should also be scaled like proportionally. So together with all these good properties, there are two families of the risk measure we are very interested in. One is convex risk measure, and the other one is coherent risk measure. So these two family risk measure, luckily, we can regard it. So when we try to calculate it, we can actually regard it to be some worst case scenario under some possible candidate Q here. So for example, for this convex risk measure, we can write it into this following form, which is a worst case scenario of all the possible measures together with a penalization term alpha to adjust this risk. If we have the coherent risk measure, we can simplify this formulation by assigning the value of the penalty to only be 0 and infinity, depends on whether our candidate is within the uncertainty set we chosen or not. So in general, in this framework, if we want to build up this equivalence between the risk measure and the worst case scenario expectation, in some of the case, for example, in this LP space, if we want our risk measure is well defined, we actually need this absolute continuity. Why? Because that for some positions that is almost they are equal almost surely, then we want our risk measure for them also equal to each other. Otherwise, without this restriction, this risk measure could depend on events that has 0 probability, right? That will lead to the inconsistency under this LP setup. So then this additional requirement is what we call the low invariant. Together with low invariant and time consistency, we want these two additional requirements. Then that will lead to one of the most important example we are going to discuss in detail, that is the entropic risk measure. So I want to emphasize here that the time consistency actually has different definition. Here we just use the equivalence between the end of time horizon and also this nested version to be our definition for the time consistency that I use in this talk. So let's take a closer look at this entropic risk measure, which again, the penalty term is defined through the KL divergence. So let's take a closer look. We can show that in the past literature that any low invariant and time consistent convex risk measure could always be written into this following form. Again, it's the combination between the worst case scenario under this Q that is absolute continuous with respect to the reference measure P, together with a penalization term, which is defined through the KL divergence between Q and P. We can also write it into this log sum of the exponential part. And then we can easily show that by citing this conditional risk measure in the nested way, we can show the equivalence, this time consistence of this entropic risk measure here. So now we actually introduce two additional requirements. One is this absolute continuity, meaning that all these candidate measures we consider, this Q, should be absolute continuity to our reference measure P, and also we enable this time consistency here. So now let's think about more about what does this about this low invariance mean, especially in the data-driven scenario. So that means that we need to first determine what is our reference measure before we doing anything else. Then from the decision-making perspective, that means that we actually assume our decision maker to be able to account for all the possible relevant risk information upfront ahead of all the decision-making process. Mathematically speaking, this means that we want to find such a reference distribution where every candidate distribution needs to be absolute continuous with. So this idea, this requirement, as noted in this paper, can be sometimes very abstract and restrictive assumption. But on the other hand, this requirement, this low invariant, actually simplifies the risk measures processes because you only focus on the law itself rather than the specific realization of it. It will be an issue, especially from the data-driven perspective, because in that setup, the reference measure P is always chosen as the empirical measure. So think about it, the empirical distribution, on the one hand, it may not be able to capture all the source of uncertainty because what happened in the past may not always represent what happened in the future. Mathematically speaking, that means that when we consider the empirical risk measure, empirical measure, the support of it may not be the entire state of the space. So it may make the decision making particularly very hard, especially if I have some new scenario happens. However, this is the issue when it applies to all the scenario tree-based computational method, because all the scenario tree based on this past data and may not be able to account for the new state in the future. So due to this mismatch between the theory and also the practice, we want to find a way to drop this low invariance requirement and allow the state beyond the support of the reference distribution. So that leads to our approach. So let's first think about in this single period case, right? So in this single period case, let's start from some empirical distribution with finite n state, and then let's think about if we assign this penalty to be only the KL divergence between, again, this reference measure to the Q, it actually penalizes the deviation of the likelihood QI and PI here. Why? You could regard it that this penalization actually only allow you to assign different probability to different states that happened before, because it fixed the state omega hat that in your past data, right? So by assigning different probability or different weights to the different states, that leads to our candidate Q here. So again, we want to find a way to enable us to think about how can we make some deviation between different states. One natural way, of course, will be that we can think about to assume this penalization term to be a Wasserstein distance between this reference measure and our Q here. Then it actually penalizes the deviation of the states of the omega hat and the omega Q here. The worst case states could be defined through this moral envelope, which again is a trade-off between this realization of your financial position and also the deviation cost. Yet, although it allows the deviation of the states, then it actually fixes the likelihoods PI that I assign to the different state here. So naturally, we can combine them together, and this penalty function, which is defined as the convolution of the Wasserstein distance and KL divergence, to allow us to do the deviation between the states and also the likelihood assigned to different states. Then we can show that in this worst case scenario, our Q here again could be regarded as a deviation from the reference measure P by do the deviation of the states and the deviation of the likelihoods. So for the single period case, this approach seems to be natural and easy to approach. So let's think about how can we extend it to the multi-period case. Because if we simply just apply this Wasserstein distance to the multi-period case, because we have no construction, no restriction on the transportation map between Q and P theta, then that may lead to some time inconsistency issue. To avoid that, instead of we just consider the Wasserstein distance, we can think about, so before we do that, let me first make some simple notation here. We can use Li to denote the likelihood ratio and Si to be the mapping between different states. With this notation, we can write that the resulting risk measure has this following form. Again, it penalizes on the deviation between the different states and also the different likelihood assigned to them. So as introduced before, to enable us to extend this case to the multi-period situation, we may, instead of consider the Wasserstein distance, here we're using this causal transport distance, which actually has been well studied among our colleagues in the mass finance group. So the causal transport distance, it's a distance extends the Wasserstein distance to the multi-period case by restricting for the transport plan to be causal. Here, the causal means that when I, for example, transport from one stage to another, the only information I can use is what happened in the past, but not the future information. So we need this time causality to enable us to write the time consistent formulation here. So we can show that by the penalty function alpha that we defined before, which again, that's the combination between the causal transport distance and also the KL divergence. We can show that the resulting multi-period convex risk measure actually admits a dynamical programming representation as follows. So as you can see, this worst case Q could be regarded again with the likelihood and also relocate the states of the conditional reference measure. So here we can similarly make the notation here. We can denote the radon-nicotine derivative between the conditional measures given this past history omega t minus 1 using this LT. And also we can define the mapping through different states using this ST here. So as you can see, both of this deviation is now only depends on the history, which again enable us to write it into this dynamical programming representation here. So now we know how to write it into this worst case scenario. Then let's move forward to think about, given this case, how can we write it as some dynamic risk measures? So let's first starting at this stage, capital T minus 1, and think about how can we measure the future risk of X capital T. So to doing that, we can using this following conditional risk mapping by defining, which is parameterized again by the history of the states up to this capital T minus 1 here. So this conditional risk mapping is defined through this conditional expectation, and we can denote this value to be some process Z at capital T minus 1. As you can see, this is itself is a filtration T minus 1 measurable random variable. So here I want to illustrate what's the mean difference between our approach to the previous multi-period approach. So in the classical way, by again allowing the entropic regularization, or by allowing the absolute continuity this requirement, that means that in this scenario tree setup, we assign different values to different nodes here, where the nodes represent the different states has a fixed value. So for each of the period, for example, from row 1 to row 2, this conditional mapping, we only change the probability assigned to the different nodes to give us what's the risk at this time period 2 here. In our method, instead of we treat each of the nodes to be some fixed value, we can treat it as the FT measurable random variable, enable us to account for both the uncertainty of the states and also the uncertainty from the likelihood. So similarly, we can define for each of the time period T, conditional on the filtration at this step, we can measure the family of the future risk into this following way, again, defined through this conditional expectation. I want to make a note here that this conditional mapping actually aggregate this FT measurable future risk at each of the steps into a smaller family of the previous measurable risk at T minus 1 here. So with this notation, we can further show that the defined risk measure using our method is time consistent, which we can again write the equivalent between the end of horizon and also this nested way. So here are some takeaways. In our framework, we discuss the equivalent, how can we define a class of multi-period risk measure, which could have the end of horizon formulation and also the neatest way that penalize both the deviation of the likelihoods and also the states. And also our approach do not depend on the low invariance this requirement. It allows the way to consider the measures beyond the absolute continuity. And this so far just we think it's a cute result, but we definitely need to do something more. For example, can we find a better interpretation to enable us to do this extension? And also our ambition here is that whether, for example, as what we can show for the entropic risk measure, can we do further? Can we say that if we want to consider the deviation for both of the likelihoods and the states, our defined class of the risk measure could actually represent the equivalent of the form of the risk measure to enable to do that. So that's basically end of my talk. Thank you again for your attention. Please let me know if you have any questions and feedback so far. Thank you.
Thank you, Luhao. Thank you for the talk. Wonderful to have you here. If you have any questions, feel free to raise your hand or type the questions in Q&A, and I can ask them. And maybe while people are doing this, I can kick off. So what I didn't quite understand was the role of the filtration and how you selected the filtration. That should be important for what are the causal relations. So somehow it would seem that how I measure risk, and maybe this is natural, should depend on what is my filtration. So how much information I observe. Where does this enter, and is that is this can you see this as a strategic decision also when you construct risk measures, and to sort of what information is included in the information stream?
That's a very good question. So unfortunately, I didn't have this. I actually didn't have the exact formulation for the filtration we consider here. And indeed, like Yang said, this is actually the key how we can do this extension here. I think it's definitely my fault. Like I didn't have the concise representation of the filtration we consider here. But quick takeaway is that enable. So as you can, yeah. So for our, let me see if I can find some oral answer for this question.
So are you only considering sort of natural filtration of some process, or is filtration sort of arbitrary and given?
So we indeed just using this natural filtration, but we need to define it through some construction that how this one depends on, for example, the realization of the omega t minus 1 and how it should then how should it formulate into the nested way enable us to do this extension. And yeah, so with this a fully adaptive filtration, that's actually the key how we can indeed make this extension. It's totally I should have the formulation for the filtration somewhere in my slides. But yeah, that's a very good that's a very good point. That's indeed the key of our construction here.
Okay. Thank you. That sounds very interesting. Do we have any other questions or comments?
I had one brief
Yes.
question. So you have this trade-off between the more KL and the more Wasserstein
Yes.
elements of your proposal. Do you have any view as to how this would relate to more statistical properties related to the training data that you're thinking through? Given if we're thinking we're going to use a point mass on an empirical measure, do you have any way of linking those types of ideas?
Yeah, that's a very good one. So in our current draft, we didn't consider many like statistic property like that, but that's definitely something we need to consider, especially, for example, one of our motivation is from the data-driven scenario with this n data points, how we can use it and to construct some practical risk measure like this. And indeed, we need to have some like statistic property, like the finite sample guarantee or something like that to be considered in the draft. That's a very good extension, and we definitely need to consider that in our in this ongoing project. Yes, thank you, Sam.
Any other questions or comments?
Maybe just a small follow-up because I had the question, but more or less was similar to Jan. Can you go a moment on the causal distance that you take from which to which? So you do causal from Q to P tilde.
Yes.
And
Which page?
just understand. Yeah, just to understand. No, maybe I think it's the next slide.
Next slide. Okay.
No, the one where you define, sorry, I don't know if you're going back and forth because I don't see the numbers. So the one where you define the causal distance, I think is you go from Q to P tilde, right?
Q to P tilde.
Your alpha?
This one?
I think the slide before, maybe.
This one, maybe then?
Yeah.
Yes, this one. So,
yes.
Yeah, so what is, because now I'm trying to understand, because of course there are many choices, right? So now
Yes.
your P is, so it makes sense, of course, with respect to P. And then you say you go causal from Q to P tilde. I don't know why I would have, because now I don't know if you tried other things, like, for example, if you tried the bicausal, or what was the choice of, like what is the choice of the causality of this direction, of this specific direction? Maybe there is an intuition, but I don't get it.
Okay, that's a very good question. So for the P tilde itself, which I didn't mention here, but this could represent, for example, as some scenario tree, the distribution of some scenario tree, which already have this the time causality itself. And then we want to see that how can we derive from the distribution of the P tilde, this scenario tree, to some candidate Q here. So enable us to do that. Indeed, we think like this one direction causal transport distance will be enough to enable, like, for example, when we do the transportation map from Q to P tilde to capture the causal time causality of the P tilde itself, then we can think like, okay, for Q to P tilde, for this stage 1 to stage 1 in Q and stage 1 in P tilde, how can we make the information like this transport map to be non-anticipative to the future outcome, right? So that way we saw like the restriction from one direction, the causality one from one to the other will be enough. And indeed, we can definitely think about if bicausal distance or the nested washes and distance, right? Are they also like a good candidate to be considered in this way? This is also some question we hope to answer, especially like when we want to say that if enable us to do this deviation from the states and the possibility, and whether this is the only choice, or it could be, or the other choice could be regarded as a modified version of this proposed risk measure, right? So that's indeed some like the future plan we want to consider in this framework.
Okay, thanks.
Yeah, but
we have a couple of hands raised.
Okay.
Natalia, do you want to go ahead?
Did I unmute myself?
Yes.
We can hear you.
Okay, so let me see the camera. Okay, so maybe I don't know why the camera is okay, it doesn't matter. So thank you, Luhao. Just if you could go back to the very original, to the very first slide where you talk about the the various over there. So you have this distinct random variables x1, and so X capital T.
Mhm.
Now, maybe I did not understand the assumptions, but are you assuming that at equals 0, you know exactly when the claim is going to arrive and when it is going to expire? So what I'm asking is that it would be nice if one could extend this kind of dynamic, if you like, decomposition, incorporating two indices in each claim, because you see claims don't always have the same initiation and the same expiration. So it seems to me that what you are doing right now is a static knowledge of claims ahead of you. So you know that you're going today, t equals 0, you know that ahead of you, you will have a claim x1 maturing at equals 1, then you will have another one maturing at equals 2, and so on. And this is information that you know today.
Mm-hmm.
But in many applications, you might not a priori know what claims you are going to encounter in the future. Does it make sense what I say?
Yes.
So I think it will be very nice to see how you could generalize. I don't think it can be done for, even if you can do it for the entropy case, that will be great. But I think perhaps that's an extension you might want to consider.
Okay. Thank you, Talia, for this
Yeah.
suggestion.
Thank you. And then we have one more question from Bruce. Bruce is an attendee. Can you? Yeah, I think you can talk now, Bruce. Right. I'm not sure Bruce is still there. He seems to be there, has a hand up, and talking is permitted, but some difficulty getting Bruce through. If you want to write your question, okay. I think we'll think there are a couple of questions on there's one more question on in the Q&A, so I'll read it. Could you explain more why you choose KL in the penalty function, which does require absolute continuity, while you mentioned at the end that the whole formulation can go beyond absolute continuity?
Could you repeat the question again? Because I don't know how to see the chat. Yeah.
Yeah. So the question was, can you explain? So the question is about KL divergence,
Yes.
and why you choose to use KL divergence. The attendee is asking, can you explain why you use KL divergence, which requires absolute continuity, while at the same time you say that you actually go beyond the absolute continuity?
Okay, so the KL divergence, we use it because that there are several reasons. Sometimes this low invariant risk requirement is a good one because that it only asks us to focus on the probability itself without like the further realization of it, right? So it sometimes will simplify the calculation, and one good example for that is the KL divergence. And also in the previous literature, they show that let me see if I, so in the past literature, they can show that for any low invariant and time consistent convex risk measure, it indeed have this, it could always have this form, right? You could always write to, for example, I have this KL divergence as my penalty here and penalize on the likelihood there, right? So by assuming this absolute continuity, I allow this perturbation from the probability I assign to different states. And then we emphasize that from the theoretical side, it's look like a good thing to have this requirement for the low invariant. However, in practice, especially in the data-driven scenario, this reference measure, which is chosen to be the empirical measure from the data, right? So sometimes you may have a new customer come to me and then you have no past data on that. If we only consider, okay, how can I assign different possibility on this new state, then there will be an issue, right? So especially in this data-driven scenario, we are thinking about how can we make our approach to be able to perturbate to different states, especially for those that never happened before in the data-driven scenario. It gave us this motivation to think about more about it, to think about how can we make the deviation not only on the probability itself, but also on the state, the deviation of the states from the previous one, right? So that's one of the motivation why we previously considered KL, because we have this nice equivalent form. And then we want to move forward to say that to address this issue, especially in this data-driven scenario, how we can overcome it using our method, right? So that's a roadmap how we can how we formulate this problem. Yes.
Great, thank you.